Welcome! Today, we'll dive into the problem titled Splitting a String into Descending Consecutive Values. This problem challenges us to determine if a string can be divided into substrings that follow a descending consecutive pattern. We'll explore different approaches and analyze their efficiency. Let's get started. In this problem, we are given a string S containing only digits, and our goal is to determine if this string can be split into two or more non-empty substrings that meet specific conditions. First, the numerical values of the substrings must form a strictly descending sequence. Second, the difference between the numerical values of any two adjacent substrings must be exactly 1. If both of these conditions are satisfied, we return true, otherwise, we return false. For example, when the input string is S equals 1234, the output is false. This is because there is no valid way to split the string into descending consecutive values with a difference of 1 between them. Now, let's look at another example. For the input S equals 050043, the output is true. Here's why: the string can be split into the substrings 05004 and 3. When we convert these substrings into their numerical values, we get 5, 4, and 3. These values form a strictly descending sequence, and the difference between each pair of adjacent values is exactly 1. On the other hand, for the input S equals 9080701, the output is false. This is because there is no valid way to split the string into substrings that meet the given conditions. Finally, consider the input S equals 100009998. In this case, the output is true. The string can be split into the substrings 100, 099, and 98. Converting these substrings into numerical values gives us 100, 99, and 98. These values form a strictly descending sequence, and the difference between each pair of adjacent values is exactly 1. This satisfies both of the required conditions, so the result is true. Now, let's go over some important constraints and edge cases. First, the length of the string S is between 1 and 20, and it consists only of digits from 0 to 9. Leading zeros are allowed in substrings, but a substring cannot consist of just 0, for example, 00 or 000 are valid, but 0 is not. For edge cases, if the string has only one character, such as S equals 1, the output is false because it cannot be split into two or more substrings. For a string with all identical digits, like S equals 11111, the output is also false, since no descending sequence can be formed. When substrings have leading zeros, such as in S equals 050043, they are valid as long as the numerical value is meaningful. Lastly, for strings of maximum length, a brute force approach becomes computationally expensive, so an efficient algorithm is essential to solve the problem. To solve this problem, one approach we can take is brute force. The intuition here is to split the string S into all possible combinations of two or more substrings and then check if these substrings form a strictly descending consecutive sequence. For example, if the string is 321, we would explore splits like 3, 2, 1 or 32, 1, and so on. After splitting, we verify whether each number is exactly 1 less than the previous number. However, there are some key observations to keep in mind. First, we must ensure every substring represents a valid integer value. Second, the descending condition requires that numbers decrease by exactly 1. Lastly, this approach becomes computationally expensive as the size of the string grows because we generate all possible splits and validate each one. The time complexity is approximately 2 to the power of n, which makes this method impractical for larger strings. While brute force helps us understand the problem, we need a more efficient solution. A better approach involves using optimized backtracking. Instead of generating all possible splits, we dynamically explore potential splits while pruning invalid options. The process begins by creating substrings of increasing length from the start of the string. Each time we construct a substring, we check if it forms a valid descending sequence with the previously chosen number. If it does, we recursively attempt to split the remaining portion of the string. If we reach the end of the string with valid splits, we return true. Otherwise, we backtrack and try other possibilities. There are several key observations that make this approach efficient. First, the descending consecutive condition ensures that, once we pick a number, the next number is uniquely defined as 1 less than the current number. Second, substrings with leading zeros, like 1 foot, are invalid and can be skipped immediately. Lastly, we can terminate early if a current split cannot possibly lead to a valid solution. This backtracking approach has a time complexity of n squared, in the worst case, as we explore splits of length 1 to n at each step. While still expensive, it is far more efficient than brute force. Additionally, we could consider an iterative approach that simulates backtracking using a stack, which avoids recursion overhead but requires careful management of edge cases. Both methods have similar complexity, but the iterative version introduces extra implementation complexity. The strategy we chose to implement is the optimized backtracking approach. This method strikes a balance between clarity and efficiency by leveraging the descending consecutive property to prune invalid splits early and minimize redundant checks. Compared to brute force, it is exponentially faster in practice, making it a much more viable solution for larger inputs. While iterative alternatives avoid recursion, they can introduce unnecessary complexity in managing the stack and handling edge cases. When considering trade-offs, backtracking stands out for its simplicity and ease of implementation, even though it may still struggle with very large strings. Brute force, on the other hand, is only practical for very small inputs due to its high computational cost. Overall, the backtracking approach offers the best combination of readability, efficiency, and scalability, making it the ideal choice for solving this problem effectively. The problem requires us to determine if a given string can be split into 2 or more substrings such that their numerical values form a strictly descending consecutive sequence. For instance, the string 54321 can be split into the sequence 5, 4, 3, 2, 1, which satisfies the condition. However, for 12345, no such split is possible. To solve this, we start by parsing the input. If the string length is less than 2, we immediately return false because at least 2 substrings are needed for a sequence. Next, we iterate over all possible lengths for the first substring, from 1 character up to 1 less than the total string length. For each length, we extract the first substring, convert it to an integer, and treat it as the starting number of our sequence. Now, we need to check if the rest of the string can form a strictly descending sequence. We initialize a pointer to track the remaining portion of the string. While there are still characters left, we calculate the next expected number in the sequence by subtracting 1 from the current number. Then, we extract the next substring, which should match this expected number. The substring length is determined dynamically based on the length of the expected number. If the substring goes out of bounds, or if the extracted number doesn't match the expected number, we end the current attempt. However, if the match is successful, we update the current number and move the pointer forward. If we successfully consume the entire string while maintaining the sequence, we return true. Otherwise, after trying all possible initial splits, we return false. This approach relies on a few key insights. First, the sequence must strictly decrease, so we dynamically compute the next number based on the current number's value and length. This ensures precise substring extraction. Second, if a split fails to maintain the sequence, we terminate early for efficiency rather than continuing with invalid checks. Additionally, edge cases are important to handle, such as strings with leading zeros, which are invalid, and very large numbers, which the algorithm must process efficiently. Finally, single-character strings where those shorter than 2 characters are straightforward to reject. The algorithm primarily uses string slicing and integer conversion to compare values, while a pointer efficiently tracks the current position in the string. Analyzing the complexity, the outer loop runs at most n times, as we attempt splits for each possible starting substring length. Within each iteration, processing the remainder of the string involves linear operations. This results in an overall time complexity of n squared. Space usage is minimal, requiring only a few integer variables and temporary substrings, leading to 1 additional space usage. We also optimize the process by dynamically adjusting the length of the next substring based on the expected number, minimizing unnecessary work. Furthermore, the algorithm exits early as soon as a sequence condition is violated, avoiding wasted computation. These optimizations ensure the solution is both efficient and scalable for large inputs. This solution uses a backtracking approach to determine whether a string can be split into descending consecutive values. Let's break it down. The split string method first defines a helper function backtrack, which is responsible for recursively checking if the string can be split from the current index onward with the condition that each subsequent number is exactly one less than the previous number. The backtrack function takes two parameters, index, which marks the starting position of the substring to process, and prev_number, the last number in the sequence that must be followed. The base case for the recursion is when index reaches the end of the string, indicating that the entire string has been successfully split into valid numbers. If this happens, we return true. Inside the backtrack function, we iterate from index to the end of the string, extracting substrings and converting them to integers, cur_number. If prev_number is none, for the first number in the sequence, or cur_number matches the condition of being exactly one less than prev_number, we recursively call backtrack with the updated index and cur_number. If any recursive call returns true, we propagate this result back up the call chain. The outer loop and split string iterates through all possible starting numbers by slicing the string at different positions, i+1. For each potential starting number, we call backtrack to test if a valid sequence can be formed. If any starting number leads to a valid sequence, we return true. If no valid sequence is found after trying all possible splits, we return false. This approach ensures that all possible splits are explored, and the condition of descending consecutive values is strictly enforced. The recursive structure naturally handles backtracking, and the loop ensures all potential starting points are considered. This is the Java implementation of LeetCode problem number 1849, splitting a string into descending consecutive values. The solution uses backtracking to explore all possible splits of the string. The backtrack method recursively validates whether a substring can form descending consecutive values. Key differences from the Python implementation include the explicit use of Java's long type for handling large values and the substring method for extracting parts of the string. To determine if the string 54321 can be split into descending consecutive integers, we begin by selecting the first number. In our outer loop, we take the first digit, which is 5, and convert it into an integer. This becomes our first underscore number. Now, we initiate the backtracking process, starting at index 1, with the previous number set to 5. The goal is to recursively explore if the remaining part of the string can form a valid sequence. In the backtracking step, starting from index 1, we extract the next digit, 4, and convert it to an integer, cur_number. We then check if this number is exactly one less than the previous number, prev_number. Since 4 is equal to 5 minus 1, this condition holds, so we move deeper into the recursion, now starting at index 2, with the previous number updated to 4. We repeat this process for the rest of the string, taking 3, 2, and finally 1, each time validating the condition that the current number is one less than the previous. When we reach index 5, which is the end of the string, all conditions have been met, and we return true. This confirms that the string can indeed be split as 5, 4, 3, 2, 1. For the input string 050403, we apply the same process to check for descending consecutive splits. Starting with the outer loop, we first consider the single-digit 0 as the initial number. However, a single-digit 0 cannot form a valid descending sequence with any subsequent numbers, so we skip this starting point. Next, we examine 05 foot, but since it contains a leading 0, this is also invalid, and further exploration is unnecessary. As we iterate through potential starting numbers, we find that none of them can lead to a valid sequence of descending consecutive integers. Thus, the result for this input is false, as no valid splits exist. Now let's analyze the string 908,070. Starting with the outer loop, we begin by taking the first digit, 9, and use it as the initial number. We then proceed to backtrack, exploring potential splits of the remaining string starting from index 1. At this point, we extract the next digit, 0, and check if it satisfies the condition of being one less than the previous number, prev_number. Since 0 is not equal to 9 minus 1, this condition fails. We then attempt to take two digits, 08 foot, but since it contains a leading 0, it is invalid, and we cannot proceed further. As we exhaust all possible splits from the starting number 9, we determine that no valid descending sequence can be formed. Therefore, the final output for this input is false. The time complexity of this solution is primarily driven by the backtracking approach used to split the string into descending consecutive values. To analyze it, we start with the outer loop, which generates potential starting numbers from the string. This loop runs for every possible length of the first number, which means it iterates up to n times, where n is the length of the string. Next, for each starting number, the backtracking function is called. Within this function, we attempt to create valid substrings starting from the current position. In the worst case, where there are no valid splits, the recursion explores all possible partitions of the string. At each level of recursion, the loop can iterate through all remaining characters in the string, leading to up to n substrings being checked per level. Since the recursion depth can go as deep as the length of the string, the total number of recursive calls grows exponentially with the length of the string, resulting in up to 2 to the power of n calls in the worst case. This exponential growth dominates the time complexity so far. Now, let's consider the integer conversion step. For each substring that we generate during backtracking, we convert it into an integer using the int function. This conversion takes time proportional to the length of the substring, denoted as k. In the worst case, we generate and convert all possible substrings, adding another factor to the overall cost. Combining this with the recursive exploration, we end up with a time complexity of 2 to the power of n asterisk n, asterisk asterisk. Here, the exponential factor 2 caret n accounts for the number of recursive calls, while the linear factor n accounts for the substring generation and integer conversion at each level of recursion. Shifting to space complexity, the primary contributor is the recursive call stack. Since the maximum depth of recursion is equal to the length of the string, the space required for the stack is proportional to n. This means the recursion stack contributes n to the space complexity. Additionally, the input string itself is stored in memory, which adds another n to the space complexity. However, this is a fixed cost and does not grow with the recursion depth, so the overall space complexity remains dominated by the recursive call stack at n. Let's now examine the best, average, and worst-case scenarios. In the best-case scenario, the algorithm quickly finds a valid split, such as on the first attempt. Here, the recursion terminates early, resulting in a time complexity that simplifies to n. For the average case, the algorithm explores a moderate number of splits before finding a solution or determining that none exist. This exploration still involves exponential growth, so the time complexity remains dominated by 2 to the power of n asterisk n, asterisk asterisk. Finally, in the worst case, when no valid splits are possible, the algorithm exhausts all potential partitions of the string. This results in the full exponential cost of 2 to the power of n asterisk n, asterisk asterisk, as every possible split is explored. When comparing this backtracking approach to a brute force method, we see significant improvements. A naive brute force solution would generate all possible partitions of the string and then validate each partition to check if it meets the descending consecutive condition. This approach would have a time complexity of 2 to the power of n for generating partitions, with additional complexity for validation, making it even less efficient than backtracking. The optimized backtracking method improves upon this by pruning invalid paths early. For example, substrings that cannot possibly satisfy the descending condition are skipped entirely, reducing the number of unnecessary computations. However, even with these optimizations, the problem's inherent complexity means that the algorithm still has exponential time complexity in the worst case. To better understand the exponential growth, we can mathematically prove that the number of recursive calls grows as 2 caret n, since each step involves considering multiple splits. Each call includes a loop of up to n iterations, adding a linear factor, which confirms the total time complexity of 2 to the power of n asterisk n, asterisk asterisk. The key takeaways from this analysis are that while backtracking is an efficient strategy for small input sizes, it becomes computationally infeasible for larger strings due to its exponential time complexity. On the other hand, the space complexity remains linear at n, as it is dominated by the recursion stack rather than any additional memory allocations. This makes the approach memory efficient compared to brute force methods that explicitly generate all possible partitions. To further optimize the solution, we would need to reduce the number of recursive calls or employ techniques like dynamic programming or memoization to avoid redundant computations. Such optimizations could help mitigate the exponential growth and make the algorithm more practical for larger input sizes. When tackling this problem, there are a few common mistakes to watch out for. First, failing to handle leading zeros can lead to invalid splits or incorrect comparisons. For instance, in the string 10,021, splitting it into 100, 02, and 1 is problematic because 02 is not a valid integer. To avoid this, ensure that substrings are treated as valid integers by skipping any splits that result in leading zeros. Next, short strings often introduce edge cases. If the string has fewer than 2 characters, it's impossible to form a descending sequence, and failing to account for this can result in unnecessary computations or even errors. A simple base condition to return false in such cases is a good way to handle this. Lastly, brute force implementations can be highly inefficient, especially for long strings. Generating all possible splits without pruning invalid candidates can cause significant computational overhead. Instead, use a backtracking approach to terminate early when a candidate split doesn't satisfy the descending condition. This not only saves time but also ensures the algorithm remains scalable. Another common issue arises with large inputs. When substrings represent very large numbers, converting them to integers can lead to overflow in certain programming languages, such as C++. To address this, you can either use string comparison to handle the values directly or rely on languages that support arbitrary precision integers, like Python. Additionally, don't assume that all splits are valid. For example, some splits might not form strictly consecutive descending sequences, and failing to enforce this rule could lead to incorrect results. To ensure correctness, it's essential to implement a robust validation step that confirms each split adheres to the descending consecutive condition. These checks are critical to maintaining the accuracy of your solution, especially for edge cases or complex inputs. From an interview perspective, this problem is often a test of your ability to implement backtracking efficiently. Backtracking is considered the optimal approach here because it enables you to dynamically split the string and validate each candidate before proceeding. This minimizes unnecessary computations by pruning invalid paths early. Beyond implementation, this problem also evaluates your pattern recognition skills. You'll need to work with substrings and recursive decision trees while identifying when to stop exploring certain paths. If you're asked about alternative methods, it's important to discuss the trade-offs. For example, while brute force covers all possibilities, it's highly inefficient compared to backtracking, which is both practical and scalable. Always clarify constraints during interviews, such as the maximum string length or whether leading zeros are allowed, as these can significantly influence your approach. Finally, related problems like LeetCode 306, 842, 131, and 282 are excellent for building familiarity with similar substring manipulation challenges. Now let's briefly explore some alternative approaches to solving this problem and their trade-offs. A brute force approach is the simplest to implement, as it generates all possible splits and checks each one. However, this method is computationally expensive, with a worst-case time complexity of 2 to the power of n. While comprehensive, it's impractical for longer strings. An iterative approach with fixed split sizes offers better performance, iterating through the string with predefined chunk sizes. However, this method lacks flexibility and may fail to handle cases where the split sizes need to vary dynamically. Its time complexity, at n squared, with optimal iteration, is an improvement but still not ideal. The most efficient and flexible solution is backtracking. By dynamically splitting the string and validating each split on the fly, it avoids unnecessary computations by pruning invalid paths early. This approach typically has a time complexity of n*m, where n is the length of the string, and m is the average size of valid splits. With these considerations in mind, backtracking emerges as the best balance between efficiency and adaptability for solving this problem. Great job! Today, we tackled the problem of splitting a string into descending consecutive values. We summarized the key insights, including edge case handling and algorithmic trade-offs. Remember, consistent practice leads to growth. Thanks for joining, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!